Hello, I'm Yaoda from the University of Hong Kong. Today, I will bring the paper Rewriting Iso-Recursive Subtyping. First of all, let me briefly introduce what is recursive types. As you can see, a recursive type has the general form mu_alpha.a, where mu is the symbol, capital A represents the type body and referred by the type variable alpha. Recursive types are used in many languages. Here is an example in Java. We define a class with a member function method. Its type is a recursive type mu_a, where the body is a row type. Not in Java or other old language, but in functional programming language, such as Haskell, recursive type is a basic feature. For example, it's a standard definition of list data structure. The type of list is a recursive type. As you can see, since type variable refers the whole type, the list can grow at every type by unfolding itself. We might want to know if two recursive types are subtypes. For example, we define two classes in a Java-like language, and they have similar structure. We wonder, is class B a subtype of class A? In Haskell, although there is no subtyping, but we could still want to know if netlist is a subtype of double list. In this talk, our main focus is Iso-Recursive Subtyping. Iso-Recursive type is a kind of recursive type. With Iso-Recursive types, a recursive type and its unfolding are only isomorphic. To convert between Iso-Recursive type and its isomorphic unfolding, explicit folding and unfolding constructs are necessary. Back to our question. How to check two Iso-Recursive types are subtype? The Amber rules are well known and widely used for subtyping Iso-Recursive types. They were briefly and informally introduced in 1985. The table on the right shows the rules about Iso-Recursive subtyping. The first one is reflexivity. The second one is assumption, and the final one is recursive rule. In recursive rule, if we want to check if two Iso-Recursive types are subtyped, we need to assume these two types are in subtyping relation by using two distinct variables, and then check the body. In assumption rule, two type variables are subtyped if they are stored in the context gamma. However, the Amber rules for Iso-Recursive type are not perfect. There are many false disadvantages. Reflexivity cannot be eliminated. It is hard to find an algorithmic formulation because transitivity elimination is non-trivial. Proofs of transitivity and other lemma is hard. Amber rules are not modular. More importantly, the meta-theory of Iso-Recursive style Amber rules is hard and underdeveloped. In this presentation, our work gives a novel declarative specification for Iso-Recursive subtyping, gives a novel algorithmic subtyping formulation using the double unfolding rule, formalizes a type lambda calculus with Iso-Recursive types and proof type soundness, and shows that our new subtyping formulation is at least as expressive as the Amber rules. We choose to use a minimal set of types throughout this work for illustration. As you can see, we have the primitive type, the top type, function type, type variable, and recursive type in our type system. Here, we see some examples to show what iso-recursive types should be subtyped. First of all, we know that any type should be a subtype of itself, wherever its type variable occurs in either covariant or contravariant position. The second one, we can see that both type variables occur in covariant position. The type of input parameter of left iso-recursive type can be any type, while the type of input parameter of right iso-recursive type is net type. Therefore, the type of left-hand side is more general than right-hand side. The last example, we see that the type variable occurs in contravariant position. We said that the type mu alpha dot alpha to net is not a subtype of mu alpha dot alpha to top. Let's analyze the third example. We want to know if left type is less than right type. Firstly, we unfold both types 1, that is, check if alpha to net is less than alpha to top. We find that the subtyping relation holds. Then, we unfold both types twice. However, in such case, the left type is not a subtype of the right type. If we continue to unfold recursive type 3 times, 4 times until m times, we find that left type is not a subtype of the right type neither. Thus, we have an important observation. In this example, one type unfolding works, m times does not. We propose a new declarative subtyping rule. If and only if all their m times final unfoldings are subtyped for any positive integer m, then two iso-recursive types are subtyped. Here is the notation of the m times final unfolding. You can easily to see that in our previous example, two iso-recursive types which have subtyping relations always meet this rule. For checking two iso-recursive types, we need to unfold it 1 time, 2 times, 3 times, 4 times, and so on. We prove some basic properties, including reflexivity, transitivity, persuasion, and progress. However, our new declarative subtyping formulation is not algorithmic. The reason is obvious. We need to iterate all the positive integer m and unfold our recursive types unlimitedly. We need to find an algorithmic subtyping formulation. Let's see this example again. After we unfold it once, we can see that alpha to net is less than alpha to top. After we unfold it twice, note that in recursive types, alpha occurs in contravariant position, so we flip the subtyping relation compared to unfold one type. In such case, for unfolding 2 times, we said that we need to check if alpha to top is less than alpha to net. If we unfold recursive time 3 times, we need to check if alpha to net is less than alpha to top, which just repeat the checking of unfolding 1 time. If we unfold recursive time 4 times, we need to check if alpha to top is less than alpha to net, which just repeat the checking of unfolding 2 times. Find times repeats 1 time, set time repeats 2 times, so on. Therefore, we can feel free to drop the unfolding k times where k is larger than 2. Our new algorithmic subtyping says we only need to check 1 time and 2 times final unfoldings. We call it double unfolding rule. It's much simple and natural. We prove that these 2 subtyping rules are equivalent. Both declarative and algorithmic subtyping are solved and complete with respect to each other. We also show that all valid-amber subtyping statements are also valid in our new Iso-Recursive Subtyping formulation. For proving this conclusion, we need a translation function to align 2 formulations. We define a function for any assumption in context. We keep the alpha and convert beta to alpha. Therefore, for a pair of iso-recursive types under amber rules, after translation, the left type doesn't change while the right type uses same type variable with the one in left-hand side. We prove that if 2 iso-recursive types are subtyped under the amber rules formulation, they are also subtyped under the double unfolding rule. Besides, in the full paper, our work proposed a new technique named subderivation for proving the declarative and algorithmic subtyping are solved and complete with respect to each other. Formalize all the lemmas and theorems in the code theorem prover. The code can be found at this link. This is my presentation today. Thank you.